Hi everyone, my name's Alex and today we're going to talk about Friedel-Craft reactions. So Friedel-Craft reactions are just electrophilic substitution where you're substituting an alkyl chain or an acyl chain. An alkyl chain is just a hydrocarbon chain, so it might be, for example, a CH3 or a C2H5. An acyl chain is a bit like a carboxylic acid but without the OH group. So because it's electrophilic substitution still, we need to generate an electrophile. So to do that we use a chloroalkane or an acyl chloride to generate our electrophile. A chloroalkane is just an alkane where one of the hydrogens is replaced by chlorine. An acyl chloride is basically like a carboxylic acid, but the OH part of the carboxylic acid has been replaced with the chlorine. When we generate the electrophile, there's heterolytic fission of the carbon-chlorine bond, and the chlorine takes both the electrons with it and leaves behind a carbocation. So the reason we use chlorine is because chlorine has a high electron affinity, so it holds the electrons really close to it, so there's already a dipole between the chlorine and the carbon, so it's much easier to generate the electrophile. Okay, so we'll do an example where we substitute a methyl group onto the benzene. So the first step we've got is to generate the electrophile. So for that we have to add chloromethane to the halogen carrier catalyst and we get the methyl electrophile, so a CH3+. The second step is to just substitute that onto the benzene. Now this bit is just the same as any other electrophilic substitution mechanism. So the electrophile will accept a pair of electrons from the ring. So now the ring is unstable and we've got a methyl group and a hydrogen attached to this top carbon. There's then heterolytic fission of the carbon-hydrogen bond, and that pair of electrons moves back into the ring and the ring is now stable. And the third step is just to regenerate that catalyst. So the hydrogen, which is expelled from the benzene, reacts with the FeCl4- and you get FeCl3 and HCl. But when you add an alkyl group, there's likely to be lots of substitutions, so you're going to get a mixture of products. And that's because each time you add an alkyl chain, some of the electrons from that chain, say from the carbon, get incorporated into the delocalized ring. So the ring has more electrons in it, has a higher electron density, and is more susceptible to being attacked by an electrophile. So to separate the products, you just use fractional distillation. The mechanism for adding an acyl group to a benzene is pretty much the same as before. So the first step is to generate the electrophile, which is just the same. So you add the acyl chloride to the halogen carrier catalyst to get your electrophile. And the second step is to substitute the acyl group onto the benzene. So the acyl group will accept a pair of electrons from the delocalized ring. The delocalized ring then reforms as the hydrogen-carbon bond breaks, and then you're left with the stable product. The third step is you just have to regenerate that catalyst as before. The conditions for acylation, which is adding an acyl group, you need to be at 60 degrees C for half an hour. It needs to be done under reflux in anhydrous conditions, and you need a halogen carrier catalyst. The reason you don't get multiple substitutions with an acyl group is because the acyl group withdraws electrons from the delocalized ring rather than donates them. So rather than being more electron dense, the ring is now less electron dense, so it is less susceptible to being attacked by an electrophile.